So this is how the frequency spectrum of practically sampled signal will look like. You can see the original spectrum is still there, and there are repetition also available of the original spectrum. This frequency point will be fs, this will be 2fs, this will be 3fs, as it is already mentioned in the form of 1 by ts, 2 by ts, 3 by ts. Similarly, minus 1 by ts will be equal to minus fs, this will be minus 2fs, this will be minus 3fs, and so on. Ideally, the maximum amplitude of all the frequency spectrum should have been constant, but due to the practical sampling in which we use a train of rectangular pulses for the sampling of the signal, you can see the locus of the maximum magnitudes, or you can say the overall amplitude of the frequency spectrum, gets multiplied by sinc function. Now we have just shown the main lobe of the sinc function. This sinc function will have the minor lobes also on both the side. So if we show few more frequency spectrum, they will be completely distorted in the signal. For example, the one which will be around 4fs will be completely distorted due to this minor lobe which is taking place here. Now we have to understand one important thing. The zero crossing point, or the ending point of the main lobe, will be nothing but inversely proportional to the width of the rectangular pulse. This will be 1 by tau here minus 1 by tau here. So if the width of the rectangular pulse is very small, or let me consider the other case first. If the width of rectangular pulse tau is very large, then 1 by tau will be very small. And if that is the case, if this point is very small, it will be close to 0, and that main lobe of the sinc function will only accommodate 1, 2, 3, maybe 3 of the frequency samples. And in such a case, because the main lobe of the sinc function will be very small in width, the distortion given to the original frequency spectrum of the signal will be very large. In this case, you can see that the original signal spectrum magnitude will not be constant. It will get attenuated on higher frequency sites due to this decreasing locus of the sinc function. But you can see for the original spectrum, this locus of the sinc function can be assumed to be almost constant. And hence I can say that the distortion in the middle, the original frequency spectrum, is very less. But the distortion in the other spectrum will be very large, but they are not useful to us anyways. But this assumption that the spectrum is almost constant, flat, cannot be made if this 1 by tau was very much close towards 0. In that case, the main lobe would be something like this, and hence you can see now the distortion due to the main lobe multiplying the original spectrum will be very large. So to avoid this distortion, the value of 1 by tau should be very large, that means away from the 0 point, and that is possible if the value of tau is very small. And that was the main condition we had mentioned. The value of tau should be as small as possible so that practical sampling resembles to very much to the ideal sampling. And ideally, if we make the value of tau equal to 0, then 1 by tau will be infinity. That means this main lobe will never reduce. There will not be any sinc function in that case. There will not be any main lobe. In that case, you will have a constant straight line, as that was the case in ideal sampling. And yes, if tau is made 0, that means the width of the rectangular pulse is 0, and hence we have achieved the presence of impulse function in that case, which practically is not possible. So that's the first type of sampling and its mathematical analysis, which is natural sampling. Let us now go through the second type, which is called flat top sampling.